This is a fun section. It's the mean value theorem, and we've seen the mean value theorem in different versions in our pre-calculus days, but here we're going to see how it could be used in calculus. So our outcomes are to explain the meaning of Rolle's theorem, describe the significance of the mean value theorem, and state three important consequences of the mean value theorem. So Rolle's theorem states that if the outputs of a differentiable function f are equal at the endpoints of an interval, then there must be an interior point where f prime of c, that is, the point x equals c, where the derivative at that point is 0. That means it's a horizontal line. And I want to just point out a couple of things here. Like, for example, these 2 points here and here would be the same. So at some point, it must go up and come back down, or like in this case, goes down and comes back up. But again, we have this horizontal line, so that slope is 0. And same thing here for this third one. So if we have, it's the same value at 2 different points of x, 2 different values of x, then it's at some point, if it's continuous, it must have either peaked, gone up and then come back down, or gone down and come back up again, such that there's a point, an extreme value that's either going to be a max or a min, but that the slope there is 0. That's Rolle's theorem. So let f be a continuous function over the closed interval ab and differentiable over the open interval ab, such that f of a equals f of b. Then there exists at least one c in the interval such that f prime of c equals 0. So you can read through the proof if you'd like. Okay, so here we go. For each of the following functions, verify that the function satisfies the criteria stated in Rolle's theorem and find all values c in the given interval such that f prime of c is equal to 0. So for a, we'll look at f of negative 2. So that's going to be negative 2 squared plus 2 times negative 2. And that's going to be 4 plus negative 4 is 0. And then f of 0 is going to be 0 squared plus 2 times 0. So that's 0. Therefore, there should be a place between negative 2 and 0 such that the derivative is 0. So our f prime of x is equal to 2x plus 2. And so if we take 2x plus 2, that derivative, and set it equal to 0, we get 2x equals negative 2, where x equals negative 1. And negative 1 falls in the interval from negative 2 to 0. So it works. Let's look at b. We'll look at f of negative 2, and that's going to be negative 2 cubed minus 4 times negative 2. That's going to be 0. We look at f of 2. That's going to be 2 cubed minus 4 times 2, and that's 0. So now let's look at the derivative. F prime of x is going to be 3, slide over a little bit, 3x squared minus 4. So our 3x squared minus 4 equals 0, so 3x squared equals 4. X squared is 4/3, so x equals plus or minus the square root of 4/3, which is plus or minus 2 over the square root of 3, or plus or minus 2 root 3 over 3. And these both fall within that interval from negative 2 to 2. So plus or minus 2 root 3 over 3 is within the interval from negative 2 to 2. Okay. I believe that value, isn't that like 0.866? I think it is. Okay, let's try another one of these. Verify that the function defined over the interval 1, 3, satisfies the coordinates, the conditions of Rolle's theorem. So we're going to look at f of 1, and that's going to be 2 times 1 squared minus 8 times 1 plus 6. That's going to be 2 minus 8 plus 6. I think that's 0, isn't it? And then f of 3 is 2 times 3 squared minus 8 times 3 plus 6. That's going to be 2 times 9 is 18 minus 24 is negative 6 plus 6 is 0. Hey, look at that. So now if we look at f prime of x, we're going to get 4x minus 8. So 4x minus 8 equals 0. 4x equals 8. X equals 2. And 2 is within the interval from 1 to 3. So it works. So we'll be talking about the mean value theorem. It's a little bit different. But it's pretty cool the way it works. And what it's really basing it on is we're looking at slope, the slope of the line, so that if you have any 2 points on that line, there's a point in between those 2 points where the slope is going to be the same as the slope on those lines. So let f be continuous on the closed interval AB and differentiable over the interval AB. Then there exists at least one point C such that the derivative at C is the same as the slope for between any 2 points on the curve. Okay, so this is an example of what they're saying. So you have a point here and a point there, and you're going to get that slope. There's going to be a point in between, like up here, where that line would have the same slope. Or even down here, that line would have the same slope. That's what the mean value theorem says. So let's do a problem with this. For f of x equals the square root of x over the interval from 0 to 9, show that f satisfies the hypothesis of the mean value theorem. And therefore, there exists at least one value c in the interval from 0 to 9, such that f prime of c is equal to the slope of the line containing 0 f of 0 and 9 f of 9. Find these values, c, guaranteed by the mean value theorem. Okay, so first thing to look at is, what's that slope going to be? Let's see what that m is going to be. Do we need to say that the square root of 0 is 0 and the square root of 9 is 3? So that's going to be like 3 minus 0 over 9 minus 0. So 3 over 9, which is 1/3. So our slope is 1/3. Now we're going to take a look at the derivative. Now my notation sometimes differs, and I have to remember to maybe use what they used. So first I want to look at the derivative f prime of x. And maybe for me it also helps to think of this as f of x is x to the 1/2. I put it in the exponential form. So the derivative is going to be 1/2 x to the negative 1/2, or 1 over 2 times the square root of x. I like to put it back in that form, in the radical form. Now, what we're after is that there's got to be a c such that f prime at c, which would then be 1 over 2 times the square root of c, equals that 1/3. And that c needs to be in the interval from 0 to 9. So let's see if we can find that. So we have 1 over 2 times the square root of c equals 1/3. And we can flip both sides. So 2 times the square root of c equals 3. Dividing by 2, square root of c equals 3 over 2. So c must be 9/4, which is 2.25. And 2.25 is within the interval from 0 to 9. That's it. And I found a someone put something together that I was able to use that anyone has access to, but it helps to illustrate this. So in this particular example, let me pull it up here. So I found this online and I put in my function. So f of x equals the square root of x. And then I have, we found a to be at 9/4. That slope will be the same as the slope between 0 and 9. And then I came down here and I came up with the equation of the tangent line. Well, not the tangent line, the secant line through 0 and 9. So this, if I turn this on here, you'll see that's the equation of the tangent line at 9/4. And if I turn this on, that's the equation of the line through 0 and 9. X equals 0 and x equals 9. So you see these are parallel lines. And that's what this is supposed to illustrate. I hope that helps. Okay. Another example here. If a rock is dropped from a height of 100 feet from its position t seconds after it is dropped until it hits the ground, is given by the position function as s of t equals negative 16t squared plus 100. Determine how long it takes before the rock hits the ground. And then find its average velocity of the rock when the rock is released and the rock hits the ground, and find the time t guaranteed by the mean value theorem when the instantaneous velocity of the rock is equal to the average velocity. So several little parts to this. Our first part, if we just take that position function and say negative 16t squared plus 100 equals 0, and we're going to solve for t, we would have negative 16t squared equals negative 100. So t squared is negative 100 over negative 16. And that can be reduced a little bit to be like 25 over, is that 4? So that t would be the square root plus or minus square root of 25 over 4. So plus or minus 5 halves. Now it can't be a negative 5 halves because we can't go back in time, so we'll go with time equals 5 halves is when this would hit the ground. So for part B, we want to get the average velocity. Excuse me. So the average velocity is going to be the position function at 5 halves minus the position function at 0 over 5 halves minus 0. So, just checking my math here. No, that's all good. Okay. So, what are we going to have there? Well, at 5 halves, we already did the math. We found that that's where the elevation was 0. So, cool. At time 0, the elevation is 100 over the 5 halves equals negative 100 times 2 over 5. And so I believe that would be negative 40 feet per second. That's our average velocity from when it starts falling. So looking at this, from there to there, the average velocity is negative 40 feet per second. Okay. Now part C says we're going to find the time at which the instantaneous velocity is equal to the average velocity. So that means we're looking for the derivative. So our s prime of t is negative 32t. So s prime of c, as the book uses, would be negative 32 times c, and that needs to equal negative 40. So dividing both sides by negative 32, c equals, and negative 40 over negative 32, that's 5/4. So that's going to be 1.25 seconds. And that's certainly within the interval we talked about, from 0 to 2.25 or 2.5. That's in the interval. That means is an element of. Okay, cool. I hope that helps. Hope that makes sense. Moving on to the last one we're going to do from this section. Suppose a ball is dropped from a height of 200 feet now. So it's a similar problem here. Find the time t when the instantaneous velocity of the ball equals the average velocity. So we're going to go through the same thing. So we have to do negative 16t squared plus 200 equals 0. So negative 16t squared plus, or is equal to negative 200. Dividing both sides by negative 16. T squared is going to be equal to, and I can reduce this down to 25 over 2. So t is plus or minus 5 over the square root of 2, or plus or minus 5 root 2 over 2. And we can drop the negative one because we can't go back in time. So now we're going to look at s of 5 root 2 over 2 minus s of 0 over 5 root 2 over 2 minus 0. And I'll be honest, I think the book did not rationalize the denominator, but I can't help it. It makes me feel awkward not to do that. So it's 0 minus 200 over 5 root 2 over 2. So that's going to be negative 200 over 5 root 2 over 2. And that would be negative 40 times the square root of 2. Now we want to look at the derivative. When's the derivative going to equal that? So we will have s prime of t is negative 32t again, because that constant just goes away. So we look at s prime of c equals negative 32c, and set that equal to negative 40 times the square root of 2. We divide both sides by negative 32. C equals, and that can be reduced down to 5 times the square root of 2 over 4. Okay, and that would certainly fall within the interval 5 root 2 over 4. Does fall in the interval from 0 to 5 root 2 over 2, because it's actually halfway in between. Okay, fun stuff. Now, this isn't quite the end of this section, it's the end of the problems, but I do want to just walk through there are some corollaries to go through at the end of this, so let's go through those. Oh, wait, there's one more problem. I didn't see that one. Okay. So this one didn't print out, but it was f of x equals 1 minus x squared, 8x squared, on the interval from negative 3 to 4. And they want us to find the point c within the interval where the derivative is slope, for the derivative would equal the average slope. So we're going to look at f of 4 minus f of negative 3 over 4 minus 3. So f of 4 is negative 127. F of, that's a negative 3 down here, minus negative 3 there. And then f of negative 3 is negative 71 all over 7. So that's negative 56 over 7, so I get negative 8. We look at our first derivative. And some c is going to be negative 16c. So we take negative 16c and set it equal to negative 8. C is negative 8 over negative 16, so c is 1/2. And 1/2 is within the interval from negative 3, I should do open interval, negative 3 to 4. Okay, there you go. Now we have a couple of corollaries, I think 3 to look at here. So let's scroll on down. Corollary 1, functions with a derivative of 0, let f be differentiable over an interval I. If the derivative is equal to 0 for all x in the interval, then f of x is a constant function. So if it doesn't matter where you go, you always have a slope of 0. That means your function's constant. It's just, f of x equals 5 or 3 or pi or something like that. Second corollary states, if f and g are differentiable over an interval I, and if f prime of x equals g prime of x, follow this, then f of x must equal g plus some constant. The constant could be 0, could be 1, could be 2, could be negative 10. And then the last one here, it's a two-parter, increasing and decreasing functions. Let f be continuous over the closed interval ab and differentiable over the open interval. If f prime of x is greater than 0 for all x in the interval, then f is an increasing function over ab. If the derivative is negative, then it's a decreasing function over that interval. Some things are probably common sense, but we're going to state them anyway. And that'll about do it for this section. Okay, see you guys in the next one, first derivative, test, and concavity.